This is problem 611. It's on page 277. Determine the force in each member of the truss and state if the members are in tension or compression. Set P1 to 600 pounds, P2 to 400 pounds. Now we are supposed to use the method of joints for this problem, and it is a bit taxing geometrically. So let's make a nice big figure that we can work with. Several geometry details to include. The structure of the truss looks something like this. Pivoted or pinned at A, pinned at E, with a 4-foot spacing horizontally between the pins, despite my drawing. And it's a symmetrical truss. Now what is not symmetrical is the loading. P1 at 600 pounds is at the center, so that's not what makes it unsymmetrical. It's this load over here, P2, at 400 pounds. Now other geometry given is that the overall height is 6 feet. And hopefully you realize that this line, since it's broken up horizontally in equal increments, then we also have 3 feet heights on that center pin. By the way, there are letters given to each pin. Let's jot down those letters. Here we are. And that's the problem that we're supposed to solve. So what I wanted to do was get some geometry for all of this, because we've got overall things, but for example, what's the length of this side, or this member, or this member? So let's see if we can figure that out. Now notice that this is a right triangle, as is this one, and therefore these two triangles, CDF and DFE, are similar triangles. Maybe not in the order of the letters that I gave them, but they are similar triangles. So if we could just figure out this triangle by itself, we'd have it. So what I chose to do is to start by considering this overall triangle. I'm going to put it right on top of the figure, because I think that's the easiest way to see this. And I called this angle over here alpha. Now, it's pretty apparent that if we've got a 3-foot height and a 4-foot side length, then we can use that information to our advantage, because we can think of breaking up this triangle into parts like this, right? We know that this height is 3 feet. And we also know that this base is 4 feet from there to there. So that means that the length of a side is 5 feet. So we know now that we've got a 10-foot length on that overall side, okay? Not really a big surprise. I mean, you can look at this length, 3, 4, 5. Okay, that makes sense. But I wanted to point out that what we really know is this base length of 4 feet here. Now, since this is in fact a right triangle, there's another triangle we can consider. Let's consider the overall triangle again. The overall thing where the base is not, well, it would be the hypotenuse in this case. So forget that 4 feet for just a second. Let's call this angle over here beta. If we now consider breaking up that right triangle into some other right triangles, just looking at these angles, you should realize this angle has to be alpha. Why? Because the original triangle had alpha 90 degrees and beta. The new triangle still has beta here at a 90-degree angle, so that side has to be alpha. Okay? And that's sort of the key to this problem. So let me highlight this new triangle in blue so it's easy to see. The angle beta doesn't matter, it just proves that the other interior angle is alpha. That's all we really need. So let's pull out this triangle and work with it just a bit. And I'll put dimensions on this figure in a moment. So what do we know about this triangle? Well, we know that this side has a length of 3 feet. We know the angle here is alpha, and so since the original triangle is a 3, 4, 5, or the other red triangle is a 3, 4, 5 triangle, and the blue triangle is similar to it because of the angle alpha, then this is also a 3, 4, 5 triangle. However, that becomes a little bit confusing. Let me just call this side y for the time being. We know it's 3 feet, but let me just call it y. Now the way this is set up, obviously the hypotenuse is the 5 side. And if you think about this, we have to rotate it to relate it to the red triangle. So this is the 4 side, this other side is the 3 side. Now we're just talking about ratios here, so what about if we scale the side lengths based on this side? So let's call this the 4 over 4 side, this is the 3 over 4, the 5 over 4 side. All we've done is multiply by a constant, and their ratios are still the same. So what's interesting about this is we can multiply y by the fraction for the side and get the length. For example, we know that y is 3 feet, 4 over 4 is 1, so this side is 3 feet. All we have to do is multiply by y on this side and y on this side, and now we have the side lengths. Now we know that y is actually 3 feet, so now we know the length of this side. It is 9/4 of a foot. And we know the length of this side, it is, since y is 3 feet, it is 15/4. Put it there. Okay? Now the whole point in doing all of that is so that we could go back to the original triangle, the one I had in red originally, or black initially, and figure out its side. So we know one side of it, 15/4 feet, 5 feet on the other, and then the hypotenuse is the sum of 9/4 and 4. So that sum, 9/4 and 4, if you do the math, what do we have? 9/4 plus 4, but 4 is, well, 16/4, right? Well, 9 and 16 are what, 25? And if you divide 25 by 4, what you'll find is 6.25. So the overall length of this side is 6.25 feet. What's interesting about this is that we end up with a 3, 4, 5 triangle. If you look at the 5 side, well, if you take 6.25 over 5, then you get the same ratio as you get with the 3, 4, 5 triangle. Anyway, we know the geometry now for all of these. So, for example, this length is 6.25 feet. There's one more bit of information that would be nice to have. Let me sketch a bigger section of the truss. This. And by the way, 15 over 4, let me just write in what this number is. 15/4 turns out to be 3.75 feet. And I don't think we need this broken up anymore, so let me just write 6.25 feet there. And we don't need any of this stuff anymore. Okay? But the length overall of this side would be 5 plus 5 is 10. We know this is 3.75 because we have similar triangles. This is 6.25, as is this one. Okay. So let me ask the question, what about this little triangle right here? It's also a right triangle. It has a hypotenuse of 6.25 feet. It's from here to here. And what about the height? Well, the height is 6 feet. So what about this base? Well, you could use Pythagorean's theorem to determine it. When I did that, I found it was 1.75 feet. Okay, so this little triangle right here was another one that I was concerned with. The reason I wanted that is because I wanted to know what this dimension is, and it's 1.75 feet. So now I think we've got all of the relevant geometrical information that we need. Not surprised, no, I didn't have to go through that. I could have simply said, well, we've got 4 feet, 4 feet is 8, minus 6.25 is 1.75. But for whatever reason, that's the way I went. Okay. So there's our geometry. Now let's continue with a free body diagram and actually get into the statics of this truss, or a static analysis of the truss. So we've got our 600-pound load external, we've got our 400-pound load, and despite my drawing, it acts directly along that line FD. We've got AY at A as well as AX. We have EX at E and EY. And so now we can start solving this truss. For example, we can sum moments about point A in order to determine, well, anything else, I guess. Sum of moments about point A taking counterclockwise as positive. What would we get? Well, notice that EX passes through that point. EY does not. AY, AX pass through. That's the whole point in taking moments about point A. It's going to be a little bit of a pain to deal with this 400-pound force, but we can do it. But we're trying to go for EY. So let's start off with that. We've got 16 foot times EY. Okay, that's the whole point in calculating this sum of moments, and EY does cause a positive moment. The 600-pound load causes a negative moment, so minus 8 foot, its moment arm, times 600 pounds. But what about this 400-pound load? Well, the key is that it acts right along this line. So coming up with its horizontal and vertical components will actually be pretty easy. Let me do this. Let's go back to that blue triangle we were talking about a little bit earlier. And let me draw it over here. It is the geometry triangle that will help us break up this 400-pound load into horizontal and vertical components. Remember the ratio of the sides. We had one side over here was the well, let's just use the geometry we have. We have a 3-foot side, 3.75 foot side, and I erased this, but it was 9/4, if you remember, okay, of a foot. And that comes out to, well, let's see, 4 away from that, so that's 2.25. So now we can use that to calculate the horizontal and vertical components of the 400-pound force. So all we have to do for this side to get the vertical component is take 400 times what? Well, multiplied by 3 over 3.75. And if you do the math, that comes out to 320 pounds. On this side, we simply need 400 times 2.25 divided by 3.75. Do the math again, that comes out to 240 pounds. And that makes our life easy because now we can, instead of considering this 400-pound force as it really is, we can consider it two separate forces, one vertical, one horizontal, in the quantity 240 pounds and 320 pounds. Now calculating the moments of these two forces will give us the same equivalent moment to the total 400-pound force, but now the geometry is easier because look, the moment arm for the 240-pound force is only 3 feet, and it is a positive moment. So plus 240 pounds multiplied by the moment arm of 3 feet, because this force acts up above the point by 3 feet. And then all we need is the moment arm for this 320-pound force, but that is 4 plus 4 plus 4 is 12. And of course it's a negative moment about A because it tends to rotate clockwise. So minus 320 pounds multiplied by 12 feet. So this moment sum, the sum of the moment of these forces, must come out to 0. So from this we can solve for EY. I won't show you the algebra, it's pretty straightforward. It comes up to 495 pounds. Basically, take this sum here, take the opposite sign of it and divide by 16, you'll have EY. So that gives us EY. Now what I'd like to do is go for another color and actually put the reactions on the diagram so that we'll have the space to solve this, because we're going to need quite a bit of space here in a moment. So 495 pounds is EY. Now, if we sum forces in the vertical direction, we should be able to find AY as well. So summing forces in the vertical direction for the overall free body diagram, now that we've broken up that 400-pound force into two parts, that should be pretty easy. So that would be what? Well, let's see. It'd be AY plus EY minus 600 minus 320 equals 0. Right? Let's see. Have we accounted for all? 600, 320, EY, AY, yes. And so solving for AY, we would get 600, well, let's just combine these two and move to the other side. So that's what, 920 minus EY, so minus 495. If you do the math, you'll find that the magnitude of AY is 425 pounds. Okay. So now we found AY and EY. What about AX and EX? Well, we can't really say much about the horizontal components of force at A and E, but we can write down an equation that we'll kind of keep in our back pocket and maybe use it later as a check or use it to calculate reactions, I don't know. But basically, if we sum forces in the horizontal direction, oh, I've just erased my free body diagram, I'm sorry. Remember there was AX and EX, and the only other component of force in the horizontal direction was the horizontal component of P2. And it was a negative component, and it would be magnitude 240 pounds. So all we have is a relationship between AX and EX from the overall free body diagram. Okay, now there's something else that we can notice here. Let's look for zero force members. We can't say that this member is a zero force member because if you think about the free body diagram of point D, which we'll get to in a moment, you realize we have P2 as well as force here. Yes, it's true, CD and DE can't apply any force in this direction, but obviously since P applies force, this member has to apply force. And actually the magnitude of the force in this member, FD, has to be 400 pounds compressive, right? That's pretty easy to see. In fact, why don't we go ahead and write that down? I kind of stole my thunder, but this must be 400 pounds and it is compressive. So I'll write in parentheses C. But notice BG, if we consider a free body diagram of point B, the line of action on C, B, and BA are collinear, and therefore, since there's no other external force, the force in BG has to be 0. It is a zero force member. Okay, so we'll start with those two. Why don't we go ahead and consider, I guess I did consider my free body diagram of D there, I just did it in my head. How about if we consider point F? Because since we know 400 pounds of compression in point F, or in member FD, we should be able to solve for the force in the other two members, FE and FC. So let's go for a free body diagram of point F and see what happens. So we know there's a compressive force of 400 pounds here acting along FD. And the question becomes, what is FE's magnitude and what is CF's magnitude? Okay. If we sum forces in the vertical direction on point F, what will we get? Well, we'll get the vertical component of the 400-pound load, which remember was negative 320 pounds. So this comes from this part. Okay. But then CF is the only other thing that can counteract it. So CFY would be the only other force. Now, how can we figure out the force or the component, y component of CF? Well, we have a triangle here to do that, right? We know that the length of this side of the triangle is 6.25 feet because it's similar to this one. We also know that the height of this triangle is 6 feet. So to get the vertical component of the force in this member, all we need to do is take 6 over 6.25. So let's make that substitution. And now from this we can solve for CF. So the force in CF would be 320 times 6.25 over 6. Okay. When you do the math, well, by the way, I'm assuming that CF is tensile. It came out positive, so it is in fact tensile. When you do the math, you'll find that the load in this member is 333.3 repeating, and of course it is a tensile load. What about summing forces in the horizontal direction? Well, there we'll have Fe minus the horizontal component of the 400-pound force, which was 240 as I recall. But notice we also have tension from CF. Let's call it CFX. So Fe, the force in that member, would be equal to 240 plus CFX. But to get the horizontal component of CF, we need 1.75 over the hypotenuse. And I erased its length, but hopefully you remember that was 6.25 feet. So since we know CF, we can plug in numbers now and find the magnitude of force in member Fe. So CF is 333, let's do it this way, 333.3 repeating. Plug that into your calculator and you'll find, of course, Fe is positive, so it's tensile, and then the load in Fe has to come out, well, ironically enough, comes out to 333.3 repeating, and it's a tensile load. All right, so that takes care of the free body diagram of F, and we've managed to find the force in 3 of the members, well, 4 so far in the overall problem. Now we'd like to know the force in these 2 members. Now notice, if you think about a free body diagram of point D, I probably should have drawn it from the very beginning. We already figured out that whatever load P is, the force in FD has to counteract it. But if you think about the load in DE and CD, well, there's no interaction here, right? These are perpendicular to one another. And so CD must be equal to DE from the free body diagram of point D, or pin D. Okay? So if I just knew the force in either CD or DE, I would know the force in the other. So what I'm going to do is consider a free body diagram of point E. So we know that CD and DE are equal. Let's just jot it down so we don't forget it. And that's from a free body diagram of point D. Let's consider a free body diagram of point E, because look, now we know EY and we know FE. And so we should be able to figure out DE. Okay? Now, there is one more force at this point, and that is EX. So what do we know, what do we not know? Well, we know FE, we know EY, and look, we should be able to get EX as well as DE. This is a good thing. So let's start off by summing forces in the vertical direction, because I'd like to get the force of the member first. And that would be equal to EY plus DE in the vertical direction, so let's call that DEY, and that's it. There's nothing else. How do I get the vertical component of this line? Well, let's see. I see a 3, 4, 5 triangle, so I need the 3/5 length. That's it. Okay. So if we then solve for DE, we'll get negative EY times 3/5. Now notice it doesn't really matter how these reactions occur. What matters is that I've plugged in the load in the member as a tensile load, and that way if I get a positive number, I know it is in fact tension. If I get a negative number, I know it is compression. I'm getting a negative number. Not surprisingly, the upper chord of this truss is most likely going to be in compression, right? That's what we expect. So this is not really a surprise. So EY has magnitude 4, well, let's not forget our negative sign, 495 pounds, take 3/5 of that, and we get the force in DE, which is a compressive force. So when I did the math, I found that the force, let me just get rid of that 5, we don't really need it right now, is 825 pounds, and that is a compressive load. Now, since we know that CD and DE are equal in force magnitude, that gives us 825 pounds compression in DE as well. And we're basically halfway through this truss, right? We've solved all of the right-hand side and one of the left-hand side. Now we can go ahead and use the fact that we've got another equation to solve for the force EX. So what would that be? Well, negative FE plus EX and minus DEX. Remember, I'm considering that DE is, or I'm assuming DE is tensile. And then when I plug in the value for DE, I'll plug it in as a negative number, right? So solving for EX from this, it would simply be FE plus DEX. Well, FE is known. The force in member FE is a tensile load, so 333.3 repeating. DE has a magnitude of 825, but it's negative, so there's my compressive load, but I only want the X component of DE. How do I get it? Well, again, remember this small red triangle was a 3, 4, 5 triangle, so I just need the 4/5 side of that. Okay. And when you plug in the numbers to your calculator, what you will find is that EX is in fact negative. So EX, I will draw it in the direction that I had on the original free body diagram, like this. But it is a negative number from this equation. It is negative 326. You know what? I don't like that. I'm going to move it down. EX negative 326.6 repeating pounds force. Now, when you plug that in for EX into this equation, solve for AX, it will yield AX. In fact, AX would be 240 minus EX, so 240 minus a negative 326.6 repeating. And when you do the math, you'll find that the value of AX is, let's see, 566.6 repeating pounds force. Now, in reality, of course, pin E is pushing this way. Both A and E are pushing this way, which makes sense. If they don't, the whole truss will just sort of collapse out of the center, right? So that makes sense. So now I'm satisfied with all of those results. Okay. So now let's continue and consider another point. Now that we've got the reaction at A, why don't we take A as our next free body diagram, or free body point. We've got what? AY, we've got AX, we've got AB, and we've got AG acting on this point. Now we know that AY is 425, and we know that AX is 566.6 repeating, and these are of course both pounds. So why don't we begin by summing forces in the y direction? Why? Because AG will not appear. I will get AB directly, and then the horizontal component of AB can be included to find AG. So summing forces in the vertical direction, I'll have 425 pounds from AY plus ABY, and that's it. There are no other vertical components of any forces on the point or on the joint. So how would I get ABY? Well, remember that this triangle is a lot like that one, right? It's a 3, 4, 5 triangle, at least to there, okay? So in order to get the vertical component of AB, I just need 3/5 of AB. So let's make that substitution. And now let's solve for AB. So AB is 425, well, negative, we got to move it to the other side, times 5/3. Okay? When you do the math, you will find then that FAB is 708.3 repeating, and it's of course negative, so that's compression. So 708.3 repeating in compression pounds force. Now if we sum forces in the horizontal direction, we'll have a X plus AG plus ABX equals 0. Okay? Now how do we get ABX? Well, again, AB is right here, so that's the 4/5 side of AB. 4/5%, or I guess 4/5 times AB. And so if we solve for AG, we get negative AX minus AB times 4/5. Well, negative of AX would be negative 566.6 repeating, but remember AB is a negative thing, it is in compression, so 708.3 needs to be plugged in negative, and then take 4/5 of it. Okay? So here is the load in member AG in pounds. So when you do the math, it turns out that the force in member AG is actually 0. Now we could have determined this in a much easier way. We could have taken point G as a free body and said, look, this is the only thing that can happen, right? There's BG, there's CG, there's AG over here, but we already know BG is not there, right? It's 0. It's a 0 force member. So there's no way that CG could have a vertical component because AG could not resist it. Therefore, CG would have to be 0, and since then the horizontal component of CG is 0, so is AG. So in fact, a free body diagram of point G would have yielded quicker the fact that AG is 0. But of course, we needed a free body diagram of point A in order to calculate the load in AB. Now notice that all these loads are 0. Basically, these members AG, BG, and CG for this particular scenario are not necessary. And so what that should help you realize is, look, if you make a free body diagram of point B, again, there's no force in BG, and therefore, whatever force there is in AB and BC would have to be equal to one another. And so, what that tells us is that this is also 708.3 repeating compression load in member BC. And so now we have solved for all of the forces in all of the members. However, it would be nice to verify that our solution is consistent, right? Consistency is truth. It's a good working definition for truth is consistency. So what point have we not taken? We haven't taken point C, have we? So let's consider point C last. There is a 600-pound load at the top of point C, and there are 4 potential loads in the 4 members pinned at C. We know we've got force in member BC. We know there's no force in member CG. We're just including it, or GC, however you like to say it. We're including it for completeness. CF has no load, and CF has a load, but we know it. And then CD. So let's just eliminate CG from our diagram because we know there's no load in that particular member. Now, of course, anytime we have a compressive load, we're simply going to plug it in as negative because we've assumed that all loads are positive. Looks like we've got 2 compressive loads, 1 tensile load. So let's check. Let's sum forces, for example, in the horizontal direction, which will not involve a 600-pound load, and let's see if things are consistent. Well, let's see. We've got in the horizontal direction, in member BC, we've got compression, so that would be, it's negative because it's in the negative direction, but the number is negative 708.3 repeating, and that's all of it. We only want the horizontal component, right? So what we've got to do is scale this component just to get the horizontal piece, so that's 4/5. That takes care of BC's horizontal component. What about CF? Well, CF is actually a tensile load, so we'll add 333.3 repeating, plug it in positive because it is tensile. Also, there's no negative sign from the free body diagram because it does point in the positive X direction. I guess we could, I should have written down a coordinate system for you. The CF is 333, but that's, we don't want all of it. We want 1.75 over 6.25, the hypotenuse. Okay? So that gives us the contribution of CF in the horizontal direction. And then finally, CD, we want its horizontal contribution. So the free body diagram says we need to add, but CD is a compressive thing, so minus 825. But we only want the horizontal component. So again, 4/5. The question is, does that equal 0? If you do the math, checks out, it works. Let's check the vertical direction. Summing forces in the Y direction. What do we have? Well, there's 600 pounds acting downward. Now it's pretty obvious. And then notice that BC acts downward, at least in the free body diagram. But BC is a negative thing, negative 708.3 repeating. We don't want all of it, we want 3/5 of it to get the vertical component. CF acts downward, so negative, but CF is actually a tensile load, so we'll simply plug it in as positive, 333.3 repeating, but we don't want all of it. We want the vertical piece of it, that's 6 over 6.25. And then CD acts downward, so negative from the free body diagram. But CD is a compressive thing, so plug in negative 825. And we don't want all of it, we just want the vertical piece, so 3/5. Does that equal 0? Well, when I did the math, let me double check to make sure I've not made a dumb mistake at the board. Yeah, when I did the math, I got 0 here as well. So that verifies that our solution is consistent, and now we know all of the reactions, AX, AY, EX, EY. We know all the force in all of the members for this particular loading scenario.